Okay, like they said, there's a few beers left over here still. If anybody wants to take this opportunity to grab one, beer makes my talk sound better. So my name's Bob Lee. I'm the CTO of a company called Square. If you don't know what Square is, we enable you to take credit card payments on your iPhone or Android phone. And we're actually right next door. This is our old office, as a matter of fact. And we use, so far as like technologies that we use Ruby, Objective-C, and obviously Java, both in our Android client and for our backend services, which is where this comes in. I'm going to talk to you about Java references. Kind of the genesis of this talk, it came from a couple places. Well, first, there's not a lot of good documentation out there on references, and a lot of the documentation that I found out there when I was first looking into this wasn't very good. Either wasn't accurate or just wasn't detailed enough. And for me, I had to learn about references for two reasons. One, I worked on the Guava project. It used to be called Google Collections. How many people have used that before? So there's Guava is kind of like the Google Commons libraries, and we have a bunch of classes in there that make it easier to use references, including MapMaker. That's a class that I wrote. And then on the other end, I was also the core library lead for a project called Android, and that meant I was in charge of like the Java compatibility libraries in Android, and I had to consult on things like the implementation of references, how the garbage collector actually handled references in the Dalvik VM, which runs on Android, and make sure that it was compatible with other Java platforms. So the goals of this talk are, one, to take the mystery out of garbage collection. When I was first starting out in programming, it was something that I ignored for a while, and then just kind of finally digging in and understanding how garbage collection worked really helped me write better code. It's not really that hard to understand when you just take a peek and look at what's actually going on under the covers. It's not magic. Two, to put an end to finalizers. I'm sure we've all heard like that advice that you shouldn't use finalizers, but we're like, oh, but it's so easy. And it's like we don't really understand the reasons not to use them, and I'm really going to drill those in and give you a bunch of reasons not to use them. And three, to learn how to, since we're not going to use finalizers, we need to learn how to do manual cleanup the right way. And the right way really depends on the context. So first of all, let's talk about how garbage collection works at a super high level. Basically, in Java, you have a heap of objects. And so these circles represent objects. They're all, and the arrows represent references between the objects. And you have this notion of root objects. And these are the objects that the garbage collector starts from. And it can have like multiple. These could be like variables, like local variables or static variables or whatever. And basically the way the garbage collector works is it crawls this graph and determines which objects are reachable from one of these roots. And basically, let me see here. If we took away a reference base from this root, like the reference between D and the root, then D is no longer reachable. And then by virtue of that, E is no longer reachable either, since D was the only object that referenced it. So those objects are no longer reachable, and the garbage collector is able to reclaim those. So what does it mean for something to be reachable? Well, the JVM defines reachable very abstractly. It's basically an object is reachable if any live thread can access it. And then the details of that tend to be left up to the implementations. And in the Java world, just some examples of heap roots or the places where the garbage collector starts. I mentioned the system classes, and if they'll have static fields that represent other objects, and then those objects will represent other objects. And then thread stacks, so like your local variables all the way up the thread stack. In-flight exceptions, that's one people typically don't think of. If you throw an exception, the garbage collector has to make sure that it doesn't free up that memory so long as that exception is in flight. JNI global references, the finalizer queue, that's one people don't typically think about. I'll talk more about that in more detail later on in the talk. The string intern pool, so it's like Java intern strings. That means it kind of like memoizes them or makes sure or like replaces all instances of strings with the equivalent values, and then other stuff depending on the VM. So garbage collection isn't a magic bullet. Like you can't just let the garbage collector manage all of your state. Sometimes you have to clean things up yourself, and like examples of that are listeners if you're doing like UI development, File descriptors are a common one. Native memory, if you're writing like library that manages native memory, you have to manually free that memory. The garbage collector doesn't know about it. And like external state, and what I mean by that is like, say, for example, I have a static map from an object to some value. Well, when that object goes away, I want to make sure that that mapping also goes away. And the garbage collector can't necessarily know to do that. So we have a few ways to clean up state. First, we have the try finally block, which I'm sure you're all aware of. We have finalizers, and which is basically this finalize method, and we have the references API, which is going to be kind of the focus of this talk. First, let's take a look at try finally. I have some example code here that basically copies a file into a given output stream. And the reason we have to use try finally is because, as you'll see here, we open the file input stream, and then we copy the data. Basically, we just read from the file and then copy that data directly to the output buffer. But we have to make sure that no matter what happens, we remember to close that file. If we don't do this, and for example, we encountered an I/O error while reading this file, then we could risk that that file not being closed, and then we'd leak a file descriptor. And if you don't know, file descriptors are a limited resource, and if you leak too many of them, your application is going to crash. So to alleviate that, we use this finally block here, and this basically ensures that no matter what, whether an exception is thrown or this returns gracefully, we close that file. So kind of the benefit here too of like closing this here as opposed to like just letting the garbage collector handle it is, if we're copying a lot of files, we could get in a state where the garbage collector can't keep up, and then we end up running out of file descriptors. You may have run into a problem like that before. So like the pros of using finally to clean up stuff explicitly is, one, it's more straightforward. You don't have to worry about like background threading and those types of concerns. You can handle exceptions in the main thread, whereas if you're doing cleanup in a background thread and it blows up, well then you have to somehow communicate that exception back to the foreground thread. And it ensures that the cleanup keeps pace. I kind of mentioned this idea of if we were just letting the garbage collector close the files, then it might not keep up and we'd run out of file descriptors. So the cons of using a finally block are, one, it's more work for the programmer. They have to explicitly write this code to close things. Two, it's more error prone. If they forget to close things, or even if they forget to close it in a finally block, they could leak that resource. For example, like I said, if reading the file throws an I/O error and they didn't close the file in a finally block, that file might not get closed. And cleanup happens in the main thread. That's a pro in the sense that it's simpler, but it's also a con in the sense that the performance overhead of cleaning up that resource is imposed on the clients of that API. So Java 7 introduced a new language feature called try with resources that makes the try finally block a little easier to deal with. So here's the code that we just looked at. You can have the try finally block that closes the file input stream in the finally block. Well, with try with resources, this code gets a lot more concise. Basically, the difference is now you can say try, and you can you open it with a parenthesis here, and now you can open up the resource. And you can open up this resource, and you can actually open up multiple resources here. But notice we don't need an explicit finally block anymore. The compiler will close this resource for us. And even better, it'll do some like really nice exception handling that that doesn't really make sense to do by hand.
Will it explicitly call close method?
He asked if it'll explicitly call close method. Yes. So this code on the bottom is semantically equivalent to this code on top. Almost. This code actually down here is actually a little better because the exception handling that's generated by the compiler is a little better than what's up here. Up here, if this throws an exception, we're going to call end.close, and if close throws an exception, that the exception that was thrown while reading is going to be just dropped on the floor, and this exception by close is going to be thrown. Whereas really, in my opinion, you actually want the original exception, not this kind of like ancillary, corollary exception that was thrown by close. So whenever you have this expression here, this is a new thing. You pass this statement as part of the try declaration. And anything that's in these parentheses will get closed.
What does it mean to get closed?
So this declaration here, so we say try file input stream, and we construct a new file input stream. This implements an interface called closable. So, and you can have any number of resources, yeah, you can have any number of resources that implement that closable interface, and they will get closed automatically at the close of this try block. So, we've talked about try finally and the benefits of that. Now let's talk about finalizers a little bit. To put it simply, a finalizer is just a callback method that's invoked before garbage collection. And this has been around before garbage collection. This has been around since Java 1.0. Let me just show you an example of what a finalizer looks like here. Finalize is actually a method on object, and all you do is you override it. And so here we have this class foo that extends bar, and it overrides the finalize method. Now this is something I wanted to point out here too. Whenever you're overriding and implementing a finalizer, you need to take care to also call your superclass's finalizer if you extend anything besides object. So in this case, we actually use finally again. We use finally with a finalizer in this case. So we do whatever it takes to clean up foo, and even if that throws even if the cleanup for foo throws an exception, the cleanup for bar will still happen. So and that's important depending on the context. So finalizers are simple. It's a simple idea. Oh, hey, just when my object, right before my object gets reclaimed, this callback gets called, but they have a lot of problems, and a lot of them like stem from the fact that, well, one, finalizers aren't very well specified, and two, you're calling, the cleanup code is on the object that you're trying to clean up. So that really opens the door to a lot of nasty surprises. So one of the first ones is the finalizer is not guaranteed to run, especially not in a timely manner. So a lot of VMs will just run all finalizers synchronously, and if one person's finalizer takes 5 minutes, no one else's finalizers are going to run until that one concludes. So, and that's actually a common problem. We ran into that on Android. Closing down SSL connections took some amount of time because it has to communicate over the network and that sort of stuff, and that prevented other things from getting finalized and ended up like locking up I/O for the whole VM. It was kind of a disaster. They have an undefined threading model, so that means, yeah, it could be single-threaded like I just described, or the garbage collector could call finalize on your objects concurrently, and if there's any interdependencies between those objects, you have to make sure that you write thread-safe code and anticipate that. You got to remember to call super.finalize like I showed in the last slide. This is kind of a funny one. Exceptions are ignored. So if you throw an exception from finalize, then the spec specifies that the VM's just supposed to drop it on the floor and ignore it. This is a big one. You can resurrect references in a finalizer. Like I said, you can, since the finalizer code is on the object that you're trying to clean up, what's to stop your finalizer from taking a reference to that object and storing it in a static field somewhere and bringing it back to life? That's called resurrection. And that's kind of a funny situation. You have this kind of like zombie object, and from my experience, the finalizer won't be called again. So you can still use the object after it was finalized, and it won't be finalized again. It's not something that you want to mess with. Even more worrisome is that obviously you probably wouldn't do anything to shoot yourself in the foot, but other people could get access to your object this way and use it to like circumvent your security and do that sort of stuff. I'll show you some examples of that here in a minute. Finalizers keep objects alive longer than necessary. So, you know, just because we're like waiting, we need the finalizer is on this object. Well, this object's queued up, and all the state associated with that object can't be reclaimed until that finalizer runs, even if the finalizer doesn't really need all of that state. So you're gonna retain garbage a lot longer than necessary and possibly even run out of memory. And Josh Block did a test for effective Java some years back and found that using a class with a finalizer is 430 times slower to allocate and reclaim than a class without a finalizer. And why is that? Well, just allocating an object and letting it get garbage collected is a really cheap operation, whereas enqueuing an object that has a finalizer and eventually running it later is not very fast. And so worst of all, in my opinion, finalizers messed up the references API because they were there, and then the references API came along later. It had to kind of accommodate finalizers, and it made the references API more complicated than it needed to be. And I'll explain how that is in a second. So let's go through an example of a finalizer. This is very similar to a lot of code that I had to write as a core library lead for Android, and where I had to wrap a lot of native APIs and that sort of thing. Managing native memory is something you have to deal with quite a bit. So I just kind of boiled this down to the simplest possible class that I could come up with. The class is called native memory. And all it does is it calls a native method that allocates some native memory, and it stores away the address for that native memory. That's what's going on right here. It just has one simple method. It enables you, it calls through to another native method to write to that native memory. We don't really have to worry about the native details. All we care about is that we've allocated some native memory and we have the ability to write to it. And this is kind of a naive implementation of a finalizer. Basically, when the finalizer gets called, we just call into native code to free that native memory. So the code looks simple enough, but let's take another look. As I mentioned before, it doesn't necessarily matter if your finalizer is safe. You also have to anticipate other people's code who may be referencing your code, and they may have finalizers themselves. So I called this code seg fault factory because it generates seg faults. And I titled this, I call this slide Let's Play War, because with this class, my seg fault factory, it will generate a seg fault 50% of the time. Just like war, you have a 50% chance of winning. In this case, you have a 50% chance of crashing your VM. So let's take a look at what this code is doing. Basically, all seg fault factory does is it references a native memory object, and it has a finalizer of its own. So, and in its finalizer, it writes to that native memory object. So what's the problem with this? That seems simple enough, right? Wouldn't you expect the garbage collector to finalize this guy and then finalize the native memory object? You get no such guarantee. I mean, like, the garbage collector isn't going to like sort your objects topologically based on which objects reference each other. It's just going to find all the objects that are finalizable at that time and start calling finalizers on them. So the odds are this finalizer can be called before the native memory one, or the native memory finalizer can be called before this one. So in this case, let's assume that the native memory finalizer is called first and that native memory is freed. What's going to happen down here? This is going to call through to that native code and write to memory that was just freed and probably seg fault your application. So how do we fix that? Always use protection. This is that same native memory class from 2 slides ago. The blue code is kind of our updated code. In this case, we can keep track of whether this object has been finalized or not, and we can change our behavior based on that. Also, we have to take care to synchronize the access to this, because the finalizer could be run from one thread, or or from multiple threads, and chances are that this write method could be being called from a different method than the finalizer. So we synchronize it. We have to synchronize both the write method and the finalizer. The finalizer sets finalized to true, and the write method checks finalizer, or checks whether it's been finalized or not. And this kind of leaves us in this weird situation too, you'll notice. If the object's been finalized and somebody calls write on it, like our seg fault factory did, what do you do? Who knows? It's like maybe you can blow up, log a message, do nothing. Doing nothing is probably not the best thing to do. And kind of the unfortunate thing here is that before, outside of this, there's really no reason for write to be synchronized. I mean, it's perfectly fine for more than one thread to write to this memory, presumably. But now we have to add the synchronization onto it just for the possibility that the finalizer may run and somebody could call it concurrently. And that's pretty unfortunate. So basically, what this all boils down to is finalizers are good for one thing, in my opinion, and that's kind of logging warnings. If you forgot to manually clean up an object. You've probably seen this with database connection pools before. If you forget to clean up your connection object, you'll get a warning. It'll say, hey, you didn't explicitly close this connection. You should fix your code. But there's also kind of a problem with that, because what happens when you want to disable the warnings? Well, now you have this finalizer that does nothing, but you still have to incur all the performance overhead that goes with finalizers. Like I said, Josh found it to be 430 times slower. The alternative, what do we do instead of finalizers? This is where the references API came in and tried to fix these problems. The references API was introduced in Java 1.2, that was a long time ago, late 90s, early 2000s, late 90s. And it introduced 3 reference types, which I'll go through. The first one is a soft reference, and this we use for caching. The second one is a weak reference. This is for quick cleanup. And the third one is a phantom reference, and this is for safe cleanup. And so that's kind of the key here. If we didn't have finalizers, we wouldn't need both weak and phantom references. And I'll talk a little bit about that. The key difference between weak and phantom references is that weak references run before the finalizer runs. So your weak references will be cleared before the finalizer runs. So your object isn't totally gone. People can still get access to it from their own finalizers. Whereas with phantom references, they aren't cleared until after all the finalizers are run. So they kind of have some of the downsides of finalizers in that you have to wait until your object's totally finalized. There's also this other concept in the References API called a reference queue. And a reference queue is how you get notified about an object, about a reference being cleaned up. So this is just kind of the API here. It's very simple. It's in the java.lang.ref package. You have a base reference type. It's just parameterized on type T. Then you have a soft reference that extends it, weak reference, and phantom reference. You'll notice that soft and weak reference, you can optionally pass this reference queue object. And that's, you only pass it in if you actually care about getting notified when that reference gets cleaned up. If you just don't want to keep a strong reference to it, you don't need to pass in a reference queue. You'll notice that phantom reference always requires you to pass in the reference queue. And this is because a phantom reference doesn't let you retrieve the original object once you've created the reference, via the reference anyway. So it doesn't make sense to have anything but a queue here. And this is the reference queue is just how you would expect a queue to look. You can pull it, or remove an element. The difference here is just that remove blocks, pull doesn't. So let's start with soft references. Soft references are supposed to be cleared when the VM runs low on memory. The spec doesn't actually make a lot of guarantees here, but they're hopefully cleared in least recently used or least frequently used fashion. There's a lot of, this is a subject of endless debate, like what's the best, and it actually really depends on your application and your context. For OpenJDK or Oracle's VM, the way soft references are implemented is they have this VM parameter called soft_ref_lir policy ms per MB. And this is soft references, least recently used policy, milliseconds per megabyte. And the idea here is you can set how many milliseconds to keep a soft reference around relative to the number of megabytes of free memory. And it's and the default is 1,000. So it'll keep around a soft reference for 1 second for every free megabyte of heap that you have. Use soft references judiciously. Frankly, you should only use them for small things. You should probably not use them at all anymore nowadays, now that there's better solutions like the caching implementation in Guava, which I'll talk a little bit about. They're good for like maybe quick and dirty caching, where you don't want to think about the size of your cache up front or something like that, and you just have small, pretty cheap objects, and you just get a small performance boost from caching those objects. A couple of the problems with soft references is, one, they have no notion of weight. All soft references in your VM are treated the same way, regardless of how much memory they take, how long they took to create. And it's like when you think about how long something takes to create, there's a difference. There's two things you have to consider. One is the amount of CPU that went into it. Did it take 100% CPU while it was doing it? Or did it just take a lot of time and not use any CPU? Or did it use 100% CPU for a long time? Those are all very different things. And you don't want some lightweight object that took a millisecond to create to be kept while the VM frees an object that took 10 seconds to create, right? Also, the way, you don't have any guarantees for the implementation. I know for at least last I checked, Dalvic's implementation of soft reference clearing wasn't that sophisticated. The OpenJDK also is really subject to problems, and we actually ran into these problems quite a bit at Google. You'll remember that I just described that that OpenJDK keeps soft references around based on how much free memory you have left. So what's going to happen as you start to converge and run out of free memory and your free space gets lower and lower? The VM keeps soft references around for shorter and shorter periods of time until you almost run out of memory and it frees all of your soft references. Well, what happens when you don't have when all your caches are empty and you don't have soft references anymore? Well, if your app continues running, it's going to have to recreate all those objects, and it's going to take a lot more time and require a lot of memory to recreate those objects, and your app just crashes. So it's kind of a disaster. There certainly could theoretically be better ways to implement soft references, but this is the reality of the situation today. So probably shouldn't use them. If you're going to use them, you can use them for small stuff. I just wanted to kind of go through a quick example here of how to use them. In this example, I call it cached file. And the idea here is we're going to cache the contents of a file in memory and just keep it around. It's okay if we have to go read the file again. It's not the end of the world. But if we read the same file a couple times, it's nice to have it. So here you can see we have a soft reference. This is a little trick I like to use here. You'll notice that I initialize the soft reference to point to a null value, and rather than just making this field null. And the reason that I did that is it avoids a null check down here a little bit later on. So we have one method, it's called getData, and this is going to get the data, read the data for that file, and copy it all into a byte array. So the first thing we do is we call get on the soft reference and get the data out. If the soft reference has been reclaimed or not initialized yet, then we're going to get null. But if it's not null, we're going to go ahead and return that data. If it was null, then we're going to initialize it. So we're going to read the data from the file, and then we're going to create a soft reference to that data. And you notice that I save it away into this reference here, and we're going to return the data. You notice that this is thread safe the way I wrote this code, and it has I kept a volatile reference to this field, which you have to do if this code's going to be thread safe. I didn't synchronize it on it, and so kind of the interesting thing there is two threads could call getData at the same time and both read the file, but that's not the end of the world. So there's a reason I picked this particular example. It's because I see people do this sometimes, but you should not do this. This whole idea of if you're just caching the contents of a file in memory, it's something that you shouldn't do, because the reality is operating systems already do a pretty good job of that for you. So if you're also caching the contents of a file in Java memory, that means you probably have two copies of that file in memory. And whereas reading the same file twice is actually a pretty quick operation, assuming you have enough memory. It's already cached. Weak references. So weak references are a little looser than soft references. They're cleared so long as immediately after no strong or soft references remain. And they're cleared as soon as possible. A common mistake is that people try to use weak references for caching, but modern VMs especially will clear these right away. So they're really not useful for caching at all. If you want to do lightweight caching, you should use soft references. Let's talk about, go through a quick example of weak references. At the beginning of the talk, I mentioned this idea of using listeners. If you write UI code, you no doubt have to do this. So we have this is a button class. This represents kind of like a button in our user interface. And it has an interface called listener that can get called back whenever somebody clicks our button. So you can add a listener, as you see here. And basically all we do is we add this listener to a list. But we don't add the listener directly to the list. If we kept a direct reference to the listener, this button would keep that listener from being reclaimed. And that would mean that you'd have to explicitly remove this listener from the button if you didn't want to have a memory leak. Whereas now that we're keeping a weak reference to the listener, once we throw that listener away elsewhere, this button will no longer notify it. And that's kind of a nice feature. So we keep a list of weak references to the listeners. Whenever somebody clicks this button, we iterate through this list. And notice I explicitly used an iterator here rather than using the for each loop. And that'll become evident, and the reason why will become evident here in a second. But we loop through the elements, and we get the next weak reference, and then we call get on that to get the listener out. If the listener was null, that means our reference was garbage collected, and we call remove on the iterator. So it gets removed from our list, and we can just get rid of that weak reference now. You got to be careful to clean up the weak reference. Otherwise, people could keep adding listeners, and those listeners could be garbage collected, but we have to make sure our weak reference gets thrown away also. So if the listener is not null, then we just call onClick on it. It's as simple as that. Finally, we have phantom references. And phantom references are like the most precarious type. They're enqueued after no other references remain. And they run, as opposed to weak references, phantom references run after the finalizer. So when your phantom reference is enqueued and you're notified that that phantom reference was cleared, you know for a fact that nobody else has a reference to that object. And that's really important from a security standpoint. So for example, we talked about native memory. For your code to be secure, you have to make sure that people can't access that native memory after it's been freed. So like an example of that is a memory mapped file in Java. Memory mapped files use phantom references under the hood. That's why you can't explicitly close them. And that's how they know to free the native memory. If they didn't do that and they didn't have the overhead of checks to see whether that memory map file was closed or not, then you could access that memory after it was freed and potentially even access memory that's being used by something else and get access to sensitive data that you shouldn't have access to. So a couple little factoids about phantom references is they have to be cleared manually, and this is really for no good reason. That means any objects that those phantom references, that phantom reference object references will be kept around even though you can't really get access to them, and that's actually due to a patent. Yay, patents. And get, I mentioned this before, will always return null with a phantom reference. So if you want to, it really only makes sense to use a phantom reference with a reference queue. So let's revisit that native memory class that we wrote before and look at how to do it the right way using a phantom reference. Like I said, we're going to use a phantom reference because we want to make damn sure that nobody has access to our native memory after we've freed it. So we're going to make a couple changes. We're going to add, whereas before we had a default public constructor, so anybody could construct our native memory directly. Now we're going to make it private. This is package private. That's the default in Java if you didn't know that. I'm going to make it package private so we can access it from our factory class, which I'll show in the next slide. We're also going to get rid of this crappy finalizer. And we're going to clean up the method. We're going to clean up the memory in a different way. So the first thing we need is a phantom reference. And the way references work is, as I said before, phantom reference extends reference, and then you can further extend that reference to store any state that you need to clean up that object. Well, what state do we need to clean up this native memory? We need the address of the native memory so that we can free it. So here we have our class. I call it native memory reference, and it extends phantom reference, and it just keeps that memory address. And that's basically all we need here. The whole purpose of this class is just to hold on to that address for us. Now, let's look at how the native memory gets allocated and freed. And so let's start here. Let's start with the allocation. So we have this factory class now called native memory manager, and this is what we're going to use to create our native memory objects. We call allocate on this. It's just a static factory method, and it returns a native memory object. This class is able to directly construct the native memory object because this is a class that manages it. It uses that package private constructor. This is kind of an interesting thing that a lot of people get tripped up with on references. We're going to construct this native memory reference, and we are going to add it to a set. So this static set, and notice that this set is synchronized so that it's thread safe. Why do we have to add this to a set? Well, you have to keep a strong reference to the reference object itself. If you don't, then the reference object just gets garbage collected and it won't get enqueued in your reference queue or anything like that. And that's actually the way you want it to behave. But you do have to remember to keep a reference around to it, your own strong reference to it. Then every time somebody allocates memory, so we create that reference, keep track of it, and then at that point, this is a common pattern, we take this opportunity to clean up any references that were cleared before this. So if we look at our cleanup method, what it does is it pulls our reference queue, which we specified up here, and any references that were enqueued, we'll take those and we'll call free on the address for that reference, and then we'll remove that reference from our set. Does that make sense to everybody what we did here? So we allocate the reference, we keep track of it, then we clean up any references that were left, and then we just return that object. And basically what's going to happen here is the garbage collector, once nobody else references this native memory object, and all the finalizers have run and all that stuff, the garbage collector is going to tell our reference queue about it. So we have this reference queue here. The garbage collector is going to tell this reference queue, and we're going to pull that reference off of the queue down here and know to clean it up. Cool. So that's how to do it with the traditional, like built-in platform libraries. The Guava libraries actually have some helper classes that make this a little easier and a little more efficient. So let's look at what this class looks like with the Guava libraries. Instead of having the reference queue, now we have a Guava-specific class called finalizable reference queue. And the difference here is rather than pulling a queue and using that model, with this we can use a callback method, and this will just be called in the background thread. There's a thread that backs this finalizable reference queue. You get one thread per queue, so you can allocate as many as you want, and you're not all on one thread like you would be with finalizers. So the allocation code changes. We can just store off the address, and we don't even need that separate reference class anymore. I'm just going to use an anonymous inner class here. Note that I still add the reference to our set. We still have to keep a strong reference to it, but now this code got quite a bit simpler. I can just put the cleanup code in this callback method here. Now, this looks like a finalizer, but why doesn't it have the problems of a finalizer? Well, it's for a number of reasons. One, I specified that we have control of the threading model now. Like, you don't just have one thread for the whole VM anymore. Two, this callback method here isn't on the object we're trying to clean up, so it doesn't have a reference to that, and you don't have that kind of impurity there. Like, this only has a reference to the address. That's all the state that it needs. So we know the object is, it's obviously correct. We know that that this code doesn't have access to the original object. So whenever the phantom reference gets cleared, this background thread, what's going to happen is it's going to pull that phantom reference off the queue and invoke this finalize referent method. And here we just free the address, and we take care to remove that reference from our set. So you can see this is quite a bit shorter. This includes both the reference class and the factory, whereas it's even shorter than just the factory before. Nice little class. Another thing that this does too that I forgot to mention is that it gets the generics correct. If you look at this, the original code that uses just the JDK classes, we have a cast here. And the reason we have this cast here is because when they added generics to JVM, they didn't parameterize reference queue correctly. They just made it of type T when you really wanted it of like some class that extends reference of type T, so that we could get our reference type off there in a type safe way. Here's a little tip too. Like I mentioned, with phantom references, if you call a get method, it always returns null. You can't get access to the original object. The original API designer was a little overzealous. He's like, I can't imagine any reason somebody would want to get access to an object that a phantom reference references, so I'm just going to totally disallow it altogether. But it just so happens I did run into a case where I needed to get a reference to the object and I wanted to use phantom references. It was in a thread local implementation for Dalvik. And basically the situation there was I had a hash table, manually implemented hash table, and it contained these reference objects. And when I'd rehash the table, when I'd have to grow it, I would have to be able to get access to the original objects. So I came up with this little trick. I call it a weak phantom reference. It's very much like a phantom reference, except it keeps a weak reference internally. So this will keep the object around long enough for us to do things like rehash a hash table and that sort of stuff. But so we can still get access to the original object so long as it's weakly reachable. Nice little tip. Don't forget, I just wanted to kind of drum this in. The garbage collector runs concurrently with our code. And when I mentioned weak references getting cleared, this is a great example here of what can happen and how fast it happens. And I've actually seen this happen. So I call this class race the collector, and it's just a little helper method. It's called let's see here. I think my battery's dying here. But it has a dereference method here, and you pass it a weak reference. And basically, what this method is going to do is if the reference is null, it's going to throw a null pointer exception. If it's not, it's going to return it. But the problem with this code here is we called get, and then we checked if it was null, but then we called get again down here. The garbage collector could have run concurrently with our code. Noticed that we don't actually use T anymore after this reference here, and garbage collected T somewhere in here. The garbage collector could run right here, and by the time this code runs, this reference could have been cleared out, and this method will actually return null, which this method is not supposed to do. So the fix for this would be to actually return T here, make sure you return T here, and so instead of calling get on the reference again. There's some higher level classes in the JDK. One of them you might be familiar with is java.util weak HashMap. Weak HashMap keeps weak references to the keys and strong references to the values. And this is useful for kind of like emulating adding an additional field to an object. So what do I mean by that? Well, you can't extend objects in Java like you can in a language like Ruby, but you could have like a static weak hash map that maps an object to a value that's associated with that object. So say I wanted to add, I don't know, like some identifier for the object. I could map the object to some identifier that I use to that object. And when that object goes away, then that it's going to be automatically removed from that weak hash map, and the value will be removed too. That's kind of the idea of those. It's useful in some situations. It's not concurrent, so you have to synchronize it. Also, this is kind of like in my original native memory manager class, it does the cleanup in line. So it only does the cleanup, it only cleans up these values when you add more, when you change that weak hash map. That's kind of a downside because it's going to keep around that value until you access the weak hash map again, when that value should be able to be cleared a little sooner than that. Another downside that I found with weak hash map, and this is a really subtle point, is that with the keys, it calls equals on the keys when I submit that it should use equals equals, because weak references are fundamentally identity based. When I'm talking about a weak reference, I'm talking about that particular instance that weak reference is pointing to, not some other instance that could be equivalent. So it's some kind of like weird subtle things happen whenever you use equality with a weak hash map. For example, like you might have a reference to a key and expect that to still be in the hash map, but it's not equivalency based, so that could be removed, and then that mapping won't be there anymore the next time you go to it. So enter Guava MapMaker. This is a class I created some time ago. It's a near drop-in replacement for weak hash map, but it's kind of a superset. It's concurrent. It's very similar to concurrent hash map under the covers, so you have like reads that don't lock and that sort of stuff. It's more featureful. Rather than just supporting weak keys, it supports strong, soft, or weak keys and or value references. And you specify those. It uses the builder pattern. It's very easy. And also, as I just talked about, it uses equals equals identity comparisons to compare weak and soft keys. MapMaker used to have some additional functionality for like, and it actually technically still does, but it's kind of it's going to go away eventually. Some like caching functionality so that you could create values on demand, but we've replaced that with a new class in Guava called CacheBuilder. And CacheBuilder is kind of a superset of MapMaker that includes all this caching related functionality. And this is probably what you should use from now on instead of soft references. So it supports on-demand computation of values. I'll show you an example here in a second, but essentially you give it a function that can take a key and return a value. And if you try to get a value out of this map and the cache doesn't find a mapping to that key, it'll use your function to create that mapping. And kind of the cool thing about it too is that it will only ever create one value per key. And this is some kind of tricky concurrency code to get right. But basically, if you have two threads that come in and try to get the same value for the same key, the first thread will start the computation, and the second thread will wait on that computation to finish. So you're guaranteed that you're only going to have one mapping per key. It also has some other cool features like expiration. You can specify that your values should expire sometime after they were added to the map or sometime after they were last accessed from the map. So that's it really depends on the situation. You need both. And the really cool feature that was added, I guess probably like 6 months ago to a year, maybe a little longer, is size limiting. And this was really the missing feature that people needed before they could really replace soft references. With CacheBuilder, you can specify the maximum size of your cache, and once you start to exceed that size, it'll remove those values. It's kind of funny. I noticed Vlad's here in the audience. He wrote the original expiration code that was in MapMaker. So here's an example of CacheBuilder in action. This example I just call this, it's like a static utility class. I'm going to call it getter methods. It has one method called on, and you give it a class and it returns you a list of getter methods in that class. So here's the example usage down here. Basically you just call getter methods on foo.class and it'll return you a list of the getter methods on foo.class. And what's a getter method? For the purposes of this slide, it's just a method that starts with get. So whenever you call this on method, it's just going to delegate straight to our cache class that we got from the CacheBuilder. Let's look how we built that up. You call CacheBuilder.newBuilder, and you can specify the keys, like the references to the keys. We have weak keys, soft values, and when we call the build method, that's when we specify the function that we use to actually create the list of methods. And this is just a function called CacheLoader from class to the list of methods. And all this does is the cache will call this method whenever it needs to create a mapping for a key. So it gets the class, it iterates over the methods in that class and picks any method that has get, that starts with get, and adds it to that list, and then returns that list. And kind of the cool thing about this is that, well, what would we have to do if we didn't use a cache here? We would have to repeatedly iterate through all the methods in the class. And if you have a lot of methods in the class that aren't getter methods, you're creating all that garbage and you're doing a lot of work. Whereas with this, we just keep that list of methods, and with this little amount of code, that value gets cached. Some interesting things. There's a reason I picked this example. There's some subtleties with classes and references. I picked weak keys. Why did I do that? Well, this is a static field. We want to keep weak references to the class objects. And the reason for that is how many people have used dynamic reloading of their web application or that sort of stuff. Well, if this class was loaded by the system class path and we kept a strong reference to a class that was in the web app class loader, well, this class would prevent that class loader from getting reloaded. And after you reloaded your web app so many times, you would run out of memory. Keeping a weak reference to that class object will enable that web app class loader to be reloaded. Now here's an even more subtle point. Why did I keep a soft reference to the value and not just a strong reference? Well, in this particular case, notice that our value is a list of method objects. Those method objects are all methods from that class. Those method objects have a reference to the class that declared them. So if we kept a weak, even if we kept a weak reference to the class itself, and we kept a strong reference to the value, we would still prevent that web app class loader from getting reloaded, right? Because you have a strong reference to the value, to the list, which has a strong reference to a method, which has a strong reference to the class, which has a strong reference to its class loader. Well, why couldn't I just keep a weak reference to the list of methods? Well, if I did that, I don't have a reference to this list of methods anywhere else. And like I said before, you cannot use weak references for caching. This would be a totally ineffective cache, and the list of methods would just be reclaimed immediately. Whereas if I use a soft reference, as I did here, then that list of methods will stick around. It's not the ideal situation. Like maybe I just want maybe I just want to keep this list of methods around permanently because I'm going to have a finite number of them. But if you want to enable reloading, you have to do this sort of thing. So does anybody have any questions about that? Cool. All right, so just to recap, the levels of reachability from strongest to weakest, this isn't exactly linear, but we'll kind of, I'll be a little hand wavy here. Strong, soft for caching, weak, which runs before the finalizer, finalizer, this is kind of you can still be referenced by the finalizer even though your object's not referenced other ways. And this is when I say that it's not exactly linear. You can go back from finalizer to being strongly referenced if you via the reincarnation that I talked about before. Phantom references, which runs after the finalizer, and then just unreachable, and that's when things can be reclaimed. So this is a little demo I like to do with this talk. It's something I came up with to kind of illustrate exactly how a garbage collector works and show you exactly what happens whenever we're dealing with these references. So here I kind of just randomly generated a heap of objects, and you can see that they reference each other. The different colored ones are references. The black ones are heap roots. So the red ones are phantom references, the green ones are soft references, and the blue ones are weak references. So I'm going to walk you through exactly how a mark and sweep algorithm works in garbage collection. This is a popular garbage collection algorithm. Pretty much all the garbage collectors in Sun's VM uses a variation of this. How many people have heard of a mark and sweep algorithm before? Cool. It's a very simple algorithm, but it's very cool. Compared to things like reference counting, it handles things like circular references really well. But the basic idea of a mark and sweep algorithm is that just periodically you have this background thread, or maybe your app just pauses periodically and does a garbage collection. So let's start off with a mark and sweep algorithm. You start off with no objects referenced. So I just kind of made them all light colored so we could keep track of which ones are referenced and which ones aren't. The first thing that the garbage collector does is it starts at a root. In this slide we just have one root, and we're going to start tracing our heap from here. We're going to trace and mark the strongly referenced objects. So here you can kind of see I'm tracing the references from objects to objects and marking the objects as I go. And so kind of interestingly here, you can see like the root has a strong reference to this object, which has a strong reference to a reference object. As I mentioned before, we have to keep strong references to our reference objects, or else they won't get enqueued. So we've traced and marked all of our strongly referenced objects. You can see like this object points to that one. None of these objects are referenced by, strongly referenced via the root. So none of these are marked yet. The next step is that we optionally clear the soft references. So in this case, you'll see that we have like a soft reference from here to this object, which isn't otherwise strongly referenced. So this soft reference could be cleared or maybe not. In this case, we have plenty of room on this slide, so I'm going to keep it around. So we'll trace and mark the softly referenced objects, and as you can see, all of these objects come back to life via that soft reference because we decided to retain it. So, and that one right there, you'll see that those pointers right there, those ones point to objects that were strongly referenced. So, basically the garbage collector is going to follow those paths and see that those objects are already marked and stop searching the heap. Next, we're going to clear the weak references. So in this case, we have 2 weak references. The one at the bottom here, you can see references an object that's already referenced, but this one at the top references an object that's not referenced. So that weak reference is going to get cleared, the one that I've highlighted in red there. And those objects aren't going to be reachable via that. Finally, not finally, actually, as you'll see in a moment, now we get to objects with finalizers. And this is where finalizers really suck. Garbage collection was simple up until this point, but now the garbage collector has to go and start with the finalizer queue. And this is just a queue, just like a queue in your own application. And the garbage collector has to put any of these unmarked objects that have finalize methods on them in the queue. Now we have to repeat all those steps that we just went through, tracing the strongly referenced objects, handling softly referenced objects, handling weakly referenced objects. We have to do that all again from the queue, from the finalizer queue. And you'll see that this finalizer queue brought all of these objects back to life. So after that, the last step is we enqueue any phantom references. In this case, we have one phantom reference here, which points to an object that's already marked. And this phantom reference points to an object that's already marked, so life isn't too interesting. None of them are going to get enqueued. All these remaining objects that weren't marked are just dead. So garbage collectors can do a couple things in this situation. One, it could manually go through and reclaim all this memory and mark it as free, all the memory associated with these objects. Or two, what's common is if you've heard of a copying collector. How many people have heard of a copying collector before? So a copying collector basically takes all the live objects and copies their memory into a new place in memory and then just frees all the old memory. And kind of the cool thing about that, it's a little more overhead in that you got to copy all that memory, but you don't have heap fragmentation. And then all those objects are gone. We clear them all out. They're gone. And we start with our heap again and we repeat. So, like I said, you start at the root, do the softly referenced objects, weakly referenced, handle the finalizer objects and repeat all those steps again. And then you handle the phantom references after the finalizer is run, and then the remaining objects are dead, and you repeat. So this is just kind of like a little tidbit. In case you're wondering whether I meticulously tweaked all those little object graphs by hand, the answer is no. I actually wrote a Java tool that generated this presentation. So I write this presentation in Java code. This is actually the code for this presentation. It's out on Google Code. It's called Crazy Bob's Talks. And in the case of, you'll see the code for this heap presentation here, I actually just created objects in memory that represented these objects and then wrote a mark and sweep algorithm. So it was a lot more fun than going through 30 some odd slides and coming up with all of those animations myself. So thank you everyone for coming. If you enjoyed this talk, I'm Crazy Bob on Twitter. If you want to learn more, I tweet about my open source projects and that sort of stuff. Also, as I said, I work at Square, we're doing tons of very cool Java code, and we do lots of cool open source projects. So if you're interested in learning more, you can email me at javajobs@squareup.com. Thanks.